In the last several lectures, we've talked about some of the ways people tried to understand the strange behaviors that were happening in a variety of systems, particularly at the atomic scale. Finally, in this lecture, we're going to talk about the real solution, quantum mechanics. Now, quantum mechanics is an incredibly strange branch of physics, but it's one that's proved enormously successful in describing things like atoms, molecules, and so many other phenomena. So as weird as quantum mechanics seems, to the best of our knowledge, it's correct. So in this lecture, we're going to introduce the basic idea of the Schrodinger equation and how this leads to quantization of energy, and we'll talk about the wave function and its probabilistic interpretation. And then we'll talk about Heisenberg uncertainty, which is one of the strange features that emerges from quantum mechanics and says that there are fundamental limits on how well we can understand aspects of the universe. So in our previous lectures, we saw several times how these same ad hoc quantization solutions worked for completely different problems. We had black body radiation, the photoelectric effect, the Bohr model. In all these cases, we made assumptions about quantization of energy or angular momentum, that only certain discrete states were allowed, and this allowed people to develop models that could explain these phenomena. And the other thing that was interesting is all these cases had this constant, Planck's constant, emerge. So as we said before, there was something fundamental going on here, but it's also clear that those models weren't correct. They were too ad hoc and made up for the individual problems. But there's clearly something missing from classical physics, and quantum mechanics is finally the theory that replaced it. So as we said, quantum mechanics is the branch of physics that describes microscopic objects such as atoms and molecules. So essentially all of chemistry is governed by quantum mechanics at the core. Now, quantum mechanical particles exhibit wave-particle duality along the lines of what we talked about in the last lecture. But the key difference here is now in quantum mechanics we have a fundamental equation, the Schrodinger equation, that governs everything. Now the details of this and solving it are far too complicated for what we want to cover in this course. We're only going to scratch the surface here, but I just want to give you a flavor of what's going on in quantum mechanics. So the Schrodinger equation is shown here. This is a somewhat schematic form though that really hides the complexity. We have H psi equals E psi. So this H is the so-called Hamiltonian. So it's actually an operator. So this is just a shorthand. There's really a lot of complications going on in here. This Hamiltonian is something that's going to take derivatives and do all sorts of other complicated things to this so-called wave function psi that it's acting on. And then this equation is saying we're looking for the wave function psi that when we act the Hamiltonian on them, we take all those derivatives and modify them in other ways, we actually end up getting back the exact same wave function times a number, which is our energy. So the Hamiltonian contains all the physics of the system, things like the attraction of the electron to the nucleus, the repulsion of electrons from one another because they're both negatively charged, etc. The wave function describes the state of the system, and we'll talk more about that in a little bit, but it's something about what the state is going on in the system, something like the Bohr orbits. And the energy is the corresponding energy of that state. So each particular wave function, psi n, has a corresponding energy, En. And the key feature here is given the nature of this equation, in solving this we are finding the different possible values of psi, the different possible wave functions and the corresponding energies that satisfy this, and each of those is going to be a discrete state. There's only going to be certain solutions that satisfy this, and those are going to naturally lead to the quantization that we've had to enforce arbitrarily previously. So quantization falls naturally out of solving the Schrodinger equation. The real hard part of quantum mechanics isn't writing down this equation. For a given atom or molecule, we can write down the Hamiltonian. It's messy and ugly, which is why I'm not showing it, but we can sit down and write it down, and it's quite straightforward to do so. But it's actually solving the equation that's very hard. So we're not going to do any of that here. But just so you know, in principle, the things we're going to be talking about can be obtained by solving this Schrodinger equation. As we're going to see, there's some really complicated and confusing things that come out of quantum mechanics, but the fact that it correctly predicts so many experimental observations is why we believe it, however unsatisfying or confusing aspects of the model may seem. So I just want to be sure, before we move on, that you're clear about what we mean by quantized or discrete states. So in classical mechanics, Newtonian mechanics, the things like balls rolling down hills, classical descriptions of light waves and water waves and so on, you have a continuum of allowed energy states. Any possible energy is going to be a potential solution to those problems. But in quantum mechanics, because the Schrodinger equation has only certain solutions, and each of those has a corresponding energy, we are only going to get certain possible allowed states of the system, and each of those has a particular energy value, so we get these discrete quantized energy states. But the key difference from this versus the Bohr model, for example, is, as I said on the last slide, that this quantization falls out naturally from solving the Schrodinger equation. One of the very strange things about quantum mechanics comes from the wave function. So the wave function really is the heart of the wave-particle duality for microscopic objects. And so the wave function might have some shape that looks like this. This is a simple 1D example just to try to give you a pictorial representation, but we might have some wave function. And the question is, how do we interpret a wave function like this? What does this mean in terms of, for example, an electron that might be bouncing around between these two walls? Well, it turns out it's the square of the wave function that gives us a probability distribution for finding the particle somewhere, finding that electron. So we might have a high probability of finding the electron here and a low probability of finding the electron here, and so on. So if this is our wave function, this is our probability distribution. But what this means is that in quantum mechanics, we lose the sense of determinism. So in classical Newtonian physics, if I throw a baseball, I can plot out and predict even a trajectory for where that baseball is going to go as a function of time. But in quantum mechanics, I completely lose that deterministic picture. Instead, all we have are these wave functions and the probabilities of finding the particle somewhere at a given time. But if we look again later, the probabilities will be somewhat different. And so this is a complete change in the mindset. We lose the ability to track individual particles, their positions, their speeds, etc., and we have to replace it with this probabilistic interpretation of trying to figure out what's the probability of finding the particle here right now, or there right now, and so on. So the wave function, as I said, is at the heart of this wave-particle duality. So the really confusing thing about quantum mechanics is how a single electron can exhibit both wave-like behaviors and particle-like behaviors. And essentially, what happens is, if we are not looking to specifically measure the property of an object, for example, we're not specifically trying to measure where the electron is, we can then have wave-like behavior that manifests. But as soon as we try to look at where it is, we see the particle-like behavior. So for example, in this electron diffraction case that I showed you in the previous lecture, if we allow the electron waves to diffract through the crystal before trying to measure where those electrons are, we can observe this sort of pattern, which is a clear manifestation of wave-like behavior. So wave functions can diffract, interfere with each other, and so on. However, as soon as we try to measure where is the particle, we get particle-like behavior. We don't measure in a single measurement some probability distribution or some wave. Rather, we see that the particle's right here, or it's right there, or it's somewhere else. We find the particle somewhere. Now, where we find it, however, is going to be random. And that random distribution is given by the probability distribution from psi squared. So we're much more likely to find the particle in regions where psi squared is large and less likely to find it in regions where it's small. But we are still, in an individual measurement, going to find that particle, that electron, in a single place. And so this is one of the features that makes quantum mechanics so confusing, that when we're not looking, things behave in a wave-like fashion, and we can see through various experiments manifestations that that wave-like behavior has occurred. But then when we go and make the actual measurement, they behave in a way that feels a little bit more like macroscopic objects, in the sense that we find a particular location for the electron or whatever. But there's this fundamental discrepancy from the macroscopic objects, that the outcomes of these measurements in terms of where the particle is are random. But quantum mechanics gets even weirder than that. There's something called the Heisenberg Uncertainty Principle that says there's fundamental limits in the universe on how much knowledge we can have about a given system. And again, this all comes from these wave functions, the wave-particle duality, and the probabilistic behavior. And so in particular, the Heisenberg Uncertainty Principle focuses on the position and the speed or momentum of the particle. So again, you can think about something like an electron. So remember that momentum is just mass times velocity. So P momentum is equal to m times v. So any measurement we make is going to have some inherent uncertainty. So let's say we measure the position, and let's just think in one dimension. So we measure the position along an x-axis, and there's going to be some uncertainty delta x. Similarly, if we tried to measure momentum, there'd be some uncertainty in the momentum, which let's just assume we know the mass perfectly well, so then the uncertainty is entirely in the speed. So we do some measurement of the particle's position and momentum, and we have uncertainties in each of those quantities in terms of how accurately we know the position, how accurately we know the momentum or speed. The Heisenberg Uncertainty Principle says the uncertainty in position times the uncertainty in momentum is greater than or equal to h over 4 pi. And the details of the exact value on the right-hand side don't matter too much. In fact, you'll see sometimes different versions of the uncertainty principle that have slight variations on what's here on the right-hand side, depending on exactly how you define the uncertainty in x and p. But the key point is that this product is greater than or equal to a non-zero quantity. And this means that there's a limit to how accurately we can know position and momentum simultaneously. To see that, let's suppose we pin down the position of the particle really precisely. We make it so that delta x for our electron is very, very small. We know exactly where that electron is. As the uncertainty here goes to 0, the only way we can make it such that this product is guaranteed to be greater than h over 4 pi is if the uncertainty in the momentum is going to infinity. So the smaller the uncertainty in position, the larger the uncertainty in momentum, or vice versa. And so this is saying that there's this fundamental limit on how much we can know about a particle's position and its momentum. Now again, remember a few minutes ago I gave the example of throwing a baseball and following its trajectory through the air. To do that, we would need to know the position of the ball and its momentum, and then we could figure out where it's going. But here, according to Heisenberg uncertainty, for quantum mechanical objects, there are limits on how accurately we can know the position and momentum, and that prevents us from ever having a trajectory that allows us to follow where an electron moves as it flies around an atom. We can figure out what's its position right now or what's its momentum right now, but by measuring one of those, we're actually losing information about the other. Now it's important to note that the Heisenberg uncertainty principle is referring to the minimum uncertainty, so the best case scenario. Of course, if you have bad experimental technique or whatever, you can have uncertainties that are even much worse. But we're saying, regardless of your experimental technique, it's impossible to know the position and the momentum with complete precision at the same time. Now this is really strange. So On this slide, I want to walk through a bit of a hand-waving justification to give you some sense of why this might be the case. So this is a thought experiment. So if we want to actually see the electron, we need some way of interacting with it and detecting it. So maybe we're detecting it with light. So we hit it with a photon of light to try to figure out where it is. And if we want a wavelength that's compatible with the sorts of wavelengths that electrons have, we'd want something like a gamma ray. Now gamma rays are extremely energetic. So this light wave here has a whole lot of energy, and when it hits this electron, it's going to impart some of that energy, some of that momentum the light wave, the photon really has, into the electron. And it's going to knock that electron off course. So even if we knew the momentum of the electron beforehand, the act of observing its position with light is going to change its momentum and therefore create new uncertainty in the momentum. We've lost information about the momentum by measuring its position because the light we used to measure its position gave some of its momentum to the electron and an unknown amount of its momentum to the electron. And so this maybe gives you a little bit of a sense of how these two ideas can be coupled and why greater knowledge of one takes away knowledge of the other. But the one thing I don't like about this hand-waving explanation or this thought experiment is that it kind of suggests that this is maybe a limit of experimental technique, that maybe we just need to find a different way to measure position. But that's wrong. It's not, uncertainty has nothing to do with poor experimental technique. The Heisenberg Uncertainty Principle is a fundamental limit of nature that's directly derivable from quantum mechanics and without any regard to what particular techniques we're using to make the measurements. It's just the universe saying there are limits on how accurately we can know these quantities. And that's completely different perspective from what we see in the macroscopic world, where it feels like we can measure everything to arbitrary precision, or at least whatever precision our experimental technique allows. But we don't anticipate there being any fundamental inherent limits on those measurements. So to see this and to see why we don't ever notice this sort of uncertainty in our daily macroscopic lives, let's do an example. Let's calculate the uncertainty in a baseball thrown at 90 miles an hour, or as we said before, that's 40 meters per second, if the speed is known to 1/1,000,000th of a percent. So in other words, let's take a best case scenario where we know the speed very, very precisely with 1/1,000,000th of a percent. That's probably far more precisely than we're ever going to bother measuring the speed of a baseball. But we just want to sort of get a case of if we minimize the uncertainty in the momentum as much as possible, that should maximize the uncertainty in the position. So let's see what happens if we do that. So our momentum is P equals M times V. So it's a 0.14 kilogram baseball. It's going at 40 meters per second. So our momentum is 5.6 kilograms times meters per second. Now the uncertainty is 1/1,000,000th of a percent. So it's 10 to the minus 8 times that momentum. So it's 5.6 times 10 to the minus 8 kilograms times meters per second uncertainty. That's the uncertainty in our momentum. Now let's solve for the uncertainty in the position of the baseball given this uncertainty in the momentum. So the Heisenberg Uncertainty Principle says the uncertainty in position times the uncertainty in momentum is greater than or equal to h over 4 pi. If I solve for the uncertainty in position, I can move the uncertainty in momentum delta p to the right hand side, plug in my numbers, plug in Planck's constant, 4 pi, my uncertainty in momentum, multiply everything out, the units all cancel properly to give us units of meters, and I get 9.4 times 10 to the minus 28 meters. Now again, remember that the dimension of an atom or a molecule, a chemical bond, is something like 10 to the minus 10 meters. So this is 18 orders of magnitude smaller than the size of an atom. So this uncertainty is utterly irrelevant on the scale of a baseball. And so this is why in our macroscopic lives, this uncertainty principle plays no meaningful role. We don't have any awareness that there might be limits on our uncertainty in position and momentum when these are the types of uncertainty limits that we would have. the error in our measurement is going to be far, far greater than any of these uncertainties and so we're never going to notice these. Uncertainty does not matter in macroscopic objects in terms of the uncertainty from quantum mechanics. Let's try another one. This one is a practice for you. So let's compute uncertainty for an electron. So let's suppose we locate that electron to within half an angstrom, which is something like a fraction of an atom. Depends on how big of an atom you're talking about, but for something like a hydrogen atom, that would be essentially enough to say, is it on the left side or the right side of the atom? So this is an atomic scale quantity. If that's our uncertainty in position, what's the uncertainty in its velocity? So here's the uncertainty principle again. Reminder for what the momentum uncertainty is defined as, and a few helpful constants and units. So go ahead and pause the video, try to solve this problem, and hit play when you're ready for the solution. Alright, so to solve this problem, we first want to rearrange the uncertainty expression to solve for the uncertainty in momentum. So delta P is greater than or equal to h over 4 pi delta x. Now I'm going to plug in the various quantities. So I'm going to plug in Planck's constant, I'm going to plug in 4 pi, and plug in my uncertainty in delta x, 0.5 times 10 to the minus 10 meters. I multiply all this out and I get my uncertainty in momentum is about 1.06 times 10 to the minus 24 kilograms times meters per second. Now I can solve for delta v, the uncertainty in the speed. So since the uncertainty in momentum is equal to mass times the uncertainty in the velocity, or speed v, I can solve for delta v. I plug in the result for the uncertainty in momentum that I computed above. I plug in the mass of the electron, and in the end, I get the uncertainty in the velocity is 1.2 times 10 to the 6th meters per second, which is about 0.04% the speed of light. So this is massive, right? Just by narrowing down the location of the electron to some fraction of the atom, we are suddenly introducing an uncertainty into its momentum that's 0.04% the speed of light. So that's a huge uncertainty into its momentum. So again, even if we know where the particle is or knew its momentum beforehand, with that amount of uncertainty in its momentum, it's going to be gone a moment from now, and we will have no idea where it is. We cannot follow its trajectory. So the uncertainty really matters in microscopic objects like electrons. And so if we think about this example just a little more, we initially, before we try to measure the position of the wave function, that electron is spread out in some fashion around the atom. Now in the next lecture, we'll talk a little more carefully about what those look like. So right here, this is just a cartoon. But we have the wave function somehow spreading that electron in some delocalized way around the nucleus. And then we want to go ahead and measure the position of the electron. And so maybe we do that and suddenly we collapse the wave function and we find the electron right here, maybe. And we have some uncertainty, say half an angstrom in that last example. And so now we know where this electron is, but the uncertainty in the momentum is huge, as we saw. So suddenly, who knows which way this electron's going? It suddenly has all this uncertainty that wasn't there before. And so an instant from now, this electron's somewhere completely different from where we thought it was. And so this is why we cannot follow quantum mechanical trajectories for microscopic objects, for things like electrons and so on. And this is all a result of Heisenberg uncertainty. So to summarize, quantum mechanics is the branch of physics that describes the behaviors of microscopic objects. It's the central equation is the Schrodinger equation, h psi equals E psi. Solving that equation gives us all the information we can get about the positions, momenta, and other sorts of properties for those particles. And it turns out that because there are going to be only certain solutions to this equation, there are only going to be certain quantized states psi, each with a corresponding energy, that are allowed. But one of the strange features of quantum mechanics is that it's probabilistic rather than deterministic, and we talked about how Heisenberg uncertainty limits our knowledge of the universe. It limits how precisely we can know position and momentum simultaneously. The more we know about one, the less we know about the other. And this is a manifestation of that wave-particle duality and the probabilistic behavior of quantum mechanics. There are a lot of other really interesting things about quantum mechanics that we don't have time to talk about in this course. Hopefully you'll get a chance to learn more in another class later. But for now, I want to leave you with the idea that despite the complexities and oddities of quantum mechanics that we just briefly touched on, it works incredibly well. It's an amazingly powerful predictive model for chemistry, and it's going to explain in the next few lectures, for example, features of the periodic table. Later on, we'll be able to use it to describe chemical bonding, and so on.